All right, I'm here for the XFLR5 tapered wing simulation tutorial. Let's get started. First things first, we want to define a airfoil. So we'll go to let's do new project, and then direct foil design. And for this tutorial, we'll do a Naka foil. So we're gonna do the Naka 4412. It's one I already have from the previous project. So I'll set that up and there we go. Now we got it, good to go. Um, Now that we have the airfoil set up, we need to start analyzing it. So we can go to the direct analysis. Um, and here we have all the polars for the different graphs, but we don't need these right now. First thing, well, all we really need to do is set up a batch analysis. This will be used for the wing design. So once we have that, click batch analysis and we select the right airfoil we want. The NOC 4412 is the one we just made. We need to define a whole bunch of Reynolds numbers that are possible for the wing to see. So we can just add some more in. Let's do let's do 8.5 to the power of or times 10 to the power of 6. And we could do another one. Again, the point of this is to create as many Reynolds numbers that the wing could potentially see. That way, when we define the analysis for the wing and it experiences very high Reynolds numbers, it knows what to do or knows how to deal with those high Reynolds numbers because we did this batch analysis for the airfoil. So right now I have it at 9 times 10 to the power of 6. That's fine for Reynolds number. We're going low speed. That'll be fine. So I'm gonna go ahead and analyze that. Let's do its thing. All right, it's good to go. And here we have the CL versus alpha, the CD versus alpha, CL CD, and then CL CD versus alpha. Right now we don't need these graphs right now because it's just the airfoil. What we're interested in are the wing analysis. So for this tutorial, we're doing a tapered wing with a specified aspect ratio. And so I have this little chart brought up or a diagram brought up. So since we're doing a tapered wing, the aspect ratio is going to be followed by this equation. And in order to get that, we need the taper ratio, which is the CT over CR. And the CT is the tip chord length, which is right here, and the root chord length is this right here, obviously. So we're going to do a tip ratio of 0.3. So if we're going to do that, then we're going to do taper ratio equals 0.3. Plug that in my calculator. And doing that, we get uh, a tip chord length of zero point 0.6 meters. Given that the root chord length is 2 meters, so if root chord length is 2, then the tip chord length is well, it's gonna not fit on the screen. Tip chord length is gonna be 0.6 for the aspect or taper ratio of 0.3, given a root chord length of 2. So that I have the CT and the CR. We can plug them into this equation to get the B, which would be the span of the wing. Since we're doing an aspect ratio of 12, we do 12 times zero point 0.6 plus 2 divided by 2, and that'll be 15.6. So we have that as our wingspan. So I'll just write that down right here. All right. Now that we have the specifications of the wing, we can actually design it. So we'll go here and do wing and plane design. Swap over to the plane module. All right, and now we need to um, now we need to actually create the wing, so or plane. So for the name, I'll just give it tapered 12, tapered wing with an aspect ratio of 12. And we're not doing the elevator, we're not doing the fin, we're just doing just the main wing. So we need to define it. So it has 2 points, one the tip and one the core root chord length. So we need to define the airfoil that we chose for both these points, which is the 4412. So we have that, and our wing is already there. And now we need to set some specifications up. We're not going to give it an offset. We're not going to do anything crazy like that. And the core length at the root is 2. So I got that. And then the core length at the tip, which we defined from the taper ratio, was 0.6. So we got that. And then we define the span as 15.6. But since this is from the root chord to the tip, it's gonna be that divided by 2, which will just be 7.8. So do 7.8. And there we have it. And we can see right here that our specifications work out. We have taper ratio of 0.3 and then the aspect ratio of 12. So everything is good to go there. So we can go ahead and save that. Now we have the wing ready to go. All right, and now we can swap over to the polars and define an analysis. So if we want to change what these graphs show, we could just double click on it and then change it to whatever we want to be. Right now I have it CL versus alpha, which is what I'm going to keep it as, but you can swap this to anything you want. It's just worth mentioning. All right, now we can go ahead and start the analysis. So we can go up there and define analysis, and then we're going to do a fixed speed at 30 meters per second. And the analysis tab, we're going to do the lifting lane theory, just LLT, and the rest of this doesn't really matter all that much. So right now that is good to go. And right now we can see the tip Reynolds number and the root Reynolds number, they're in the millions, which is why we defined the BATS analysis from before. That's where this comes in handy. So we can save that. And my analysis is going to be from an alpha of -5 to 20 degrees, increment of 1. We can see that right here. And we can go ahead and start that. So we can see that it calculated for each point. And just due to the nature of this wing shape that we designed, it didn't converge at alpha is equal to 19 and 20. That's fine. We don't. That's just inherent from the wing design. It's not a big deal. But here we go. Now that we have all our data, we can see it on these graphs. And if we want to export these graphs, we can do so pretty easily. All we need to do is go to here and then export the results. And we can just call this tapered 12 for the same name as the wing. So now that we have that, we can go here, we can open that up, and we have all of our data right here. We have the alpha, the CL's induced drag coefficient, the wave drag, and the induced, as well as the base drag. And the rest of this we don't really need for this video, so I'm gonna go ahead and just delete that. And realistically, we don't even need the CDI and CDV. Those are just combined into the CD total. All right. So now we can go ahead and start analyzing and creating some plots for the data. We'll just recreate what we saw in XFLR5, but we'll create it in Excel. That way we can utilize it or analyze it more. So to do that, I'm going to go ahead and create a chart. Any of them really, doesn't really matter which one. Just got to start with a blank one. The series, and this one was the tapered. I'm just going to call it TAP 12. Um, and so X value, we'll set that as the angle of attack. And then for the Y, we will just do, let's do the first one, which is the coefficient of lift. And that way we have this nice graph. You can see that right here. For the CL, let's see. I probably should actually rename this, not just TP, but CL versus alpha. All right, there we go. And once we have this, we can, add a trend line and do a lot more of analyzing as opposed to just the graphs in XFLR5, which is why it's useful to have or know how to create these in Excel. So let's go ahead and create the other graph. We can just copy and paste this one as a template. And this one we'll do CD versus alpha. All right. And for this one, I'm gonna go ahead and select the data. Go ahead and edit what we already have. X value remains the same, that's just the alpha, but we'll change the Y. And the Y will be, there you go. So we've got that good to go. Let's go ahead and zoom out a little bit. Let's go ahead and create one more. And this one, let's see, what do we have? We'll do the CD, or sorry, CL versus CD graph for this one. So we're going to go ahead and change the data immediately. So this time we need to change everything here. So the CL will be the x-axis and the CD will be the y-axis. There we go. And go ahead and change these titles. This is the CL and the CD. All right. Now for the final graph, we need to do the CL over CD versus the alpha. So we can do that. We can define an equation for that real quick. So this one will be equal to, we'll do inside those brackets, do CL, which was C8, and then divided by the CD, which was F8. And there we go. And then we could just shoop, drag that down, and now we have that good to go. So now we can create our final graph. Which is let me just rename this first. Oops. All right. CL over CD. And all that remains is to change the data. All right, so X value remains the same for this one as the first two, but we could change the Y, which was what we just created. All right, and there we go. Now that we have everything there, we can compare it. And yeah, we have pretty much the same data there. Everything looks good. Um, CL versus CD was swap, I think. I think the CD should be on the bottom, but that's fine. Um, and yeah, that is pretty much it. Any other analysis we want to do now, we can go ahead. If we want to define more wings, we can create more wings in SFLR5, wing shapes, maybe not tapered or with a twist, and keep on importing them into here. and we can add these plots onto here for comparative study. Pretty much anything you want to do, you can do from here. And yeah, that's about it for now. Um, Thank you for watching.